Okay, so I'd like to welcome everyone for the new semester here. Hope you're gonna have an awesome semester together. My name is Amir Ashuri. I'm a postdoc researcher at the University of Toronto. This semester I'll be a sessional lecturer of this course at York. So since I wasn't an employee of York, my account hasn't been set up, so I couldn't set up the website page at York. But by the next week, I'll let you know, guys, by an email or some sort of communication. We'll figure it out where the website would be and how we're going to proceed with that. All right. So for now, before the website starts, either the wiki page or I guess you call it Moodle here. If something happened and I couldn't reach you out, please check my webpage at uToronto. So if I couldn't figure out something, I'm gonna post either the slides or some notices there. But I was just talking with one of the IT technicians, so they're gonna set that up soon. So we'll be able to have another web page at York, hosted by York. Also, your TAs will be announced by next week. We're gonna have a meeting with all of our co-lecturers. So it's a pretty huge group of students. In this section, I believe we have more than 100 students. This is the same for the other two. So we have a pool of TAs. So we are trying to, sort of manage the workload for TAs for your labs as well. I guess most of you know that you have labs. So I have to ask the guys that just go to your own assigned lab. So you can just check on your semester schedule and then see if you are in O1 or O2. And both of them are happening in the same place but different days, because we are in limited seats. We would like everyone to attend their own sessions, because if you submit your lab assignments in the other session that you weren't supposed to, you might have issues with the gradings and so on and so forth. I guess the first lab we're gonna have will be in 2 weeks, so not next week. We'll be starting our labs in 2 weeks. I'll post another notification before that, so so you guys will be informed. Basically, what we're gonna do is you're gonna have 8 labs, so 4 before your midterm and 4 after your midterm. And for each of those 4, if somebody couldn't attend one lab for any emergency reasons, we're gonna have another makeup. So 1 makeup for each of your 4 labs. So 1 makeup before your midterm and 1 makeup lab after your midterm towards your final. And during each lab, you're gonna have you're gonna be given some instructions, and you're gonna have a pre-lab, which is following through that instructions using the software tools, the simulator that has been built at York. It's a RISC V simulator. I'll describe it in details later. So you're gonna follow through the instructions, and you would do your pre-lab assignments. You submit assignments. After that, we're gonna put the lab machines in the test mode, and in the test mode, you're gonna basically follow through with what you've been doing in a pre-lab, but as a sort of a test environment. And you're gonna be evaluated both on your pre-lab and your test submission after that. So this is going to be for one of your labs. So we're going to have lab 1, 2, 3, 4 before the midterm, and then 5 to 8 after your midterm. So so that's just the general high-level idea of what we're going to do with the labs. For the reference of the textbook, I'm sure you've seen this. How many of you have already obtained this? Okay. So this is computer organization and design for the RISC V edition. In the past, it used to be the MIPS edition, but the authors switched from the MIPS architecture which was done in the like 80s and 90s, pretty famous and popular. Recently to RISC V. So RISC V is an open source architecture designed by University of Berkeley with many collaborators all over the world. And now they have released the RISC V edition. It's a more simplified version, I would say, of the MIPS. So they have changed this book, the authors, they've changed it to the RISC V version. Basically, we are trying to conform with the structure of the book with some little tweaks, but mostly that's going to be your reference. So I've also put a tentative schedule, but this is subject to change, so it's going to change definitely, and we're going to update it every time. So basically today, I didn't mention here because it was just the introductory course. I didn't want to use all my time, so starting from next week, you're gonna carry on with chapter 1, and we start chapter 2. Then we go towards the rest of chapter 2, and probably here, because of your first lab, I'll switch some initial courses about chapter 3, and then we switch back to chapter 2 because it's gonna help you to follow through with your labs. So in 2 weeks, as I mentioned, we're gonna have our first lab, and then going forward up to the reading week, which will be no classes, and then after that we're gonna have the midterm after that. So that's gonna be a rough and tentative schedule for this semester. Okay. So the course prerequisite is just a general. Yeah, good.
You said in 2 weeks, lab start. That's the 16th to the 20th.
I believe so. Yeah. Yeah. No problem. So I wasn't at York before, so perhaps you had some prerequisites in order to get this course. So what was that prerequisite?
1021. Yeah. Java, object-oriented code work.
Okay. Yeah. So you don't need. You just need basic understanding of programming. I mean, we mostly work with the RISC V simulator, so that I just put a screenshot here. So this is the high-level view of that simulator. So basically, you're going to input an assembly source code. I'll explain what that is if you don't know what assembly is. And then it's going to generate you some lower level instructions that we're going to use in the course. So as an example, so suppose you add I instruction for 2 registers, and then it's gonna translate into this unknown notation that you have no clue right now, but you're gonna learn what those things are working. And then the rest of the windows are for memory and other things. So on your lab session, we're gonna mostly working on that, and we assign you some task to do, and you're gonna have the output of this, and you're gonna report it back normally. So the grade composition would be mostly, I simplified it, 30, 30, 40. Probably it's going to fluctuate a little bit, -2, -3% up and down, but the labs are roughly around 30%. So each lab considered around 5%, 4%, and then you have midterm and final. Any questions? I saw it. Yep. Yeah.
You said there would be quizzes and stuff. Does that include the lab?
I'll see if that makes it, better to have quizzes or not. I haven't decided on that, but for now, assume you don't have quizzes. You just have pre-labs and lab assignments. More questions? Okay. All right. So the description of your course is, as I mentioned, is based on RISC V. It's the first architecture that has been designed to be used in modern computing. It hasn't been realized completely yet on a real hardware, but there are many universities and research institutes working on that. It's getting pretty popular. It has its own advantages. We're gonna touch on those, and it has a simplistic sort of design, which is much better currently than the ARM base or the MIPS base, which was there in the past. So, what you will learn by the end of the course. So you're going to understand, first of all, in computer organization and architecture, you're going to understand what's happening inside your computer. So it's as if you're zooming into your processor and see what's happening underneath when you write a high-level language. And it's going to give you a pretty good idea of, what's happening inside the box. So we are just opening that box and looking into that. So basically, by opening that box, you're going to understand how the programs are translated from a high-level language like C, C++, Java, to a lower level language that machine understands that, right? And not only that, how the hardware underneath your computer executes them, right? So you're going to learn about hardware and software interface, and what actually determines the program performance. Are we talking about how fast a program runs, how accurate the program runs, how fast the tasks within that or processes within that program runs, or do we compute that based on the processor that was assigned to that? So there are different methods for that. And finally, you understand how hardware designers improve performance such a way. Okay, so these are just some high-level points, just to set up your mind in order to carry on the course. So we had many different revolutions in the past, I would say 70 years of introducing computers, starting from the early 50s, late 40s. And so these are some of those. But one of the most important ones are the computers that are anywhere now. They're used in embedded world. They are used in mobile domain. So they're everywhere. That's why they call it pervasive. So they are in everyday life. It's in your smartwatch. It's in your cell phone. So each of those has a different hardware and architecture and design. So this is one of the most important, I would say, revolution of computers in history. So in the past, we had a third class of computers in between these two, but not anymore now. So it was the PC, it was the personal computers. But nowadays, by the advancement of the embedded world, those are smaller chips, like your cell phone, your smartwatch, basically that middle class is gone, and they have diverged into two different extremes. So we have supercomputers now, or we have embedded computers. So in the supercomputers, we have the high-end scientific world that mostly they're using that, thousands and thousands of core. If you just go to top 500 website, basically every 3 months or every 6 months, I guess if every 3 months they're gonna list the top 500 supercomputers of the world. So you can see how many cores, how many petaflops, how many computations per second they can handle, and they're gonna put it in they're fighting to get into that list. Also, there is another list for top 500 green computers, which the most performant computers regarding the energy efficiency. So there are two different computing lists. And for virtually for countries, it's very important to top that list. and you can see, if you see the trend, in the past it used to be like United States in the top 5. Now we have Japan, we have China, and other actors that are trying to build, better and more performant supercomputers. On the other side, when you look into the embedded world, embedded computing, so we have another class of computers that are very, very popular today. So if you look at this, so the y-axis represents the number of devices in millions that are sold. So you see the PC is probably plateaued somewhere. Tablet, at some point it got super popular, and then it came back down. So now, perhaps in the future, we have a sort of a super group of tablets and smartphones. And then PCs are, as I mentioned, plateaued. So you see the trend here. So, and I'm sure you've heard about cloud computing, so I'm just not gonna spend more time on that. So many of the services you've been using in the past, in your personal computer, in your local internet, in your local workstation, now they have been turned into services, and they are used in a cloud-based manner, right? So when in this course, when we talk about performance, you need to ask yourself, because we are opening the boxes, we are understanding what's beneath the computer. You need to be asking yourself where it comes from. Is it coming from the algorithm? Is it coming from the specific programming languages that we are using? Is it coming from the memory hierarchy of the system using different cache sizes? Or is it coming from the I/O, the input-output of that system? And that we include that OS inside that. So we're going to touch on all of those, and you're going to have a clear idea of when we talk about an organization of a computer, what components are actually having the, having to play the sort of roles into running a software in certain speed or in certain performance. Right? Okay. Any questions so far? So these are some jargons that you're going to see more in this course. So Moore's law. Does anyone know what Moore's law was? Okay. Can you?
The number of transistors inside the chip doubles every certain frequency.
Yeah. That was okay. Any more explanation you can get? So basically, in the late 60s, Moore was the researcher who brought this law. He was basically extrapolating and seeing the trend in the industry that every certain month, 18 months or so, the number of transistors are getting doubled within the same area. That means that their speed was getting doubled every certain months, which on that time he was predicting every 18 months. So that given the same size, if you fix the size, your speed will become double and double. Or on the other hand, you can half the size with the same speed. So your devices would shrink. And he was extrapolating in up to mid-2010s, and he basically says that if we carry on this trend for these upcoming 50 years, 40 years, at some point the laws of physics cannot allow us to have transistors closer to a certain threshold. Otherwise, they're going to lose their physical, nature of a transistor, because they're so close that you can't play around as a switch for that. So that got famous for Moore's law, and it was basically one of the roadmaps of computer designers. We're gonna talk about it more, but later on, when we reached to the limit of Moore's law, we understood that that was not the single issue that the computer architecture and the industry was facing. After mid 2000s, like 2007 and 8, when Intel started to generate multi-cores, a whole slew of issues brought up. So how are you going to have the performance via parallel cores? Either have a different multi-core or each of the cores have different processors inside. How are we going to handle the hierarchy of memory? So my L1, L2, and L3 caches, how am I going to play with those in order to have a faster programs? So all of these ideas we're going to touch in this course, and I hope you're going to have a much better idea of thinking about how a program runs in a computer after the course. So basically, by computer architecture, we are spanning right from the hardware up to the application software. So this is basically those layers that the computer architecture is looking into. So you have your hardware that runs your software, right? And you have a system software in between, could be anything. So computer architecture is the study of the amalgamation of sort of these three and spans from software ends to the hardware. So let's just have a quick example. You're going to learn about all those details. Just don't freak out by seeing this. It just shows you that starting from a high-level language, in this case it was C, you could just change it with C++, C#, Java, or anything. So you have a swap function. So you want to swap the values of V, K. So you need to have a temporary variable, and then you swap these two. So what's happening when you compile this? Use a compiler to run it onto your machine, right? Because obviously the machine don't understand anything about swap. I mean, the machine only understands a binary code, which is this. So the process that we take from a high-level language up to a binary code, so it is done via compilation, right? You compile your code, you come into an assembly language somewhere in between these two, still readable. We're gonna learn how to read that. It's still readable. And then after that, the assembler is going to generate that binary machine readable code for you. So basically, this job of the assembler is done by in your lab when you are doing your lab projects. Basically, you don't have to translate this to this. That's the job of your RISC V simulator. But in the past, believe it or not, like in 20 years ago, to 25 years ago, 30 years ago, when the compilers were not that optimal, many of the engineers had to just manually write this. Or just like in your first page of your book, if somebody told me he already obtained the book. So the first page is a green page with all the assembly language sheet for the RISC V. You see, it's a green page. So it was called green card in the past. So they could fold it in their pocket, and then at some point they had to just open it up and then see, oh, this instruction will translate perhaps to this. So I have to write that because there was not an optimized compiler to do that. But now we are lucky. Everything has been optimized. We're just learning how it is done. Okay. So, the component of your computer, if you, as an analogy, if you take a look at your computer, this could be a representative of that. So you have an input-output, right? You input something to that, and then it's going to output something. Right? Along the way, this chain has to be controlled, right? And using the data path, we can understand what data we're going to process and what data we're going to output, right? The right side will represent your memory because it's going to deal with anytime you want to do something, you want to load something, you want to save something, you have to load it from memory and you want to save it back to memory. There are some faster sort of faster memories, let's say, in a high level speaking, and we call it cache. So, but they're very limited, they're expensive. In general, you have to load variables from memory, manipulate them, and then save them again. And the component that does that manipulation, calculation, and control is your CPU, right? Is your processor. And here we are standing here and pinpointing the issues and understanding how we're going to evaluate the performance of this tool chain. Input, process, and output. So in a high level manner, so your data path performs operation in your data. The controls that sequence of data path, and your cache, which was your faster memories, you can use it in your benefit in order to speed up your program, right? So we call it SRAM. The good old memory, we call it DRAM in the past. All right. So in computer architecture, we are really interested in abstractions because we are somewhere in between hardware and software, right? We are trying to find a way to have some sort of representation of a computer that doesn't change every time you change your hardware and every time you change your software, right? We want something independent from those beneath. So one of the perfect ways to define that sort of abstraction is by defining it using an ISA or ISA, some might say, which we call it instruction set architecture. So this is the interface that you're going to see more and more in this course, and each architecture represents its own ISA. So when we are telling you that this is an ARM-based architecture because it has its ARM ISA. When we say in this semester we are talking about the RISC V because we are targeting towards RISC V ISA, right? It has its own set of abstractions. Intel machines have their own abstractions, ISA as well. So by having this, you're no longer dependent to your hardware and software beneath. So using that, you can abstract the process and workflow of the instructions that are needed to be run on your hardware, okay? All right. That's just a trend of technology. So early 90s refers to vacuum tube. If you just normalize it and give it 1 as the performance of your baseline performance, let's say, you see that by 2013, how many order of magnitudes the performance has been improved by having the latest generation of ultra-large scale ICs. So I'm not going to go into details because it's just an introductory chapter, but in general, the whole processing element comes from this simple notion. So you have silicon, which is coming from the sand. So a company such as Intel, they can refine the sand and extract the alloy, and I'll show you the process in the next slide. And make something like this, which is sort of a switch. We call it silicon, and it's a semiconductor. Okay. So depending on how we're gonna switch those and make them positive and negative, so that represent N and P, we're gonna have different switches. So at some point we can design an amplifier with that. Another thing, we can design a switch for that. And this switch is gonna act as when certain voltage passes, it's gonna turn it on and it's gonna turn it off. So the whole 0 and 1 you saw on that binary, output of your high-level language, all those 0 and 1s are going to get executed in such a way. It's pretty intuitive. So let's talk about how they're going to get into that, right? So they start from the ingot silicons. They're coming from sand, so huge pile of sands. They are doing different filtering. And then they slice those, and then they make a blank wafers. So they repeat this process many times, and they pattern those wafers, and start testing to see, after adding those elements, how many of those are going to be workable and how many are not. And that's why we have the Yale sort of metric. So the proportion of working dies per wafer. So say if out of 6, 5 of them are working, you see 5 out of 6, right? So one out of 6 wasn't working, so wasn't yielding performance. And that's pretty much what it takes if you zoom in to 300 millimeter. So that's a 32 nanometer technology. So you have now better even 9 nanometer in your cell phones or CPUs. So it has gone a long process in order to make it to here. I'm not sure if I can run this here, but we'll see. What is it? Yeah. I embedded here. So it should be a YouTube placeholder. Yeah. Let's see. Let's see if we can run it on the browser.
Yeah.